Hi everyone. Today I'm going to be modeling a continuous beam using a continuous plasticity nonlinear finite element analysis program. I'm doing this because I get lots of requests from viewers. They want to see more modeling examples using free software. The educational version of this program is available. I'm going to discuss that, so you should be able to do this analysis. I looked at my library to find an example which is sophisticated enough but also doable within a limited video time, and I found this example from this textbook in case you want to see the reference. This could be for a performance-based design, or this could be for an existing structure, because in existing structure it's really difficult to pass. If you do the inelastic analysis, nonlinear will give you an idea. Is it failing in shear? Is it failing in flexure? What's going on? What are the loads? What are the crack widths? And you can make an appropriate decision depending on the results. This beam has 5 spans. It's symmetrical. That gives us an advantage. We can only model half of it. Cross section 900 deep, 600 wide. Let's look at the question. We are not going to be doing the full question, but we would be going through the nonlinear modeling process. We are only looking at the single load case, which is fully loaded, 120 kilonewton per meter, uniform distributed load. This already has load factors applied. Part A, bending moment diagram using a linear elastic analysis. Of course, we are going to be doing nonlinear analysis. That's the whole point of the video. Determine the required tension reinforcement. We cannot do this using nonlinear analysis. So you need to know the reinforcement and then model it. That's why I selected this problem, because it gives certain options for the reinforcement quantities. So part C, consider 3 alternatives. Which solution is most suitable for this design based on your design calculations? I picked option 2, so this is the one I'm going to be modeling using a nonlinear finite element analysis method, and the method I'm going to be using is a rather sophisticated method developed at the University of Toronto. Several graduate students, master, PhD, contributed to the development of this program. I also made a lot of effort during my PhD studies. And you can see the theoretical basis. This is rather sophisticated. It uses modified compression field theory. It considers shear as well as flexure. And more importantly, this is a distributed plasticity model. You do not define any hinges. It can consider plastic deformations at any point. So you don't have to make any assumptions or any estimates. You can look at the theoretical basis. This is the flow chart. There's a lot of iterations going on to satisfy conditions of equilibrium, compatibility, as well as constitutive relationships. You can see cross-section. It could be a T-section, I-section, rectangle, circle. You can define it in any way you like. These are strain distributions. You can see concrete response, reinforcement response. It considers strain hardening as well. So this is really what we are doing. If you are doing a monotonic analysis, this is yielding, yield plateau, and then it goes into strain hardening and ultimately rupture taking place. There are also other things as well. So you can visit my website and you can download all these papers. You can also do a Google search and you should find all of these freely available. This is application. So there are some applications in this paper as well. This is another paper which looks at cyclic load conditions using this procedure. We call this vector 5 because we have, a suite of vector programs. Each one does something different, and vector 5 is for beams, columns, shear walls, and frames in general. So this is a simple example for vector 5 because I'm going to be modeling a beam only, continuous beam. The program is available for download. It has a limited number of elements, but it should be enough to model continuous beams, columns, shear walls, etc. So that might be good for your educational purposes. There is a paid version, which is the full version. We intend that to be for consultants. If somebody is earning money, definitely we expect some contributions because we need to fund students to work to advance these programs. So significant time, significant expenses occurred during development, and we would like to develop these any further. All right, so that's enough talking. I would like to get started with this one, but your support is really important because videos are very, very time consuming. At least like the video, write some comments, and also if you would like to see other types of modeling, if you would like to see more of Vector 5 modeling some other systems, please let me know. The model would be created using Formworks Plus. These are all together, so you would feel that they work as if there was a single program, but there are three programs in fact. Formworks Plus will do the modeling, Vector 5 analysis, and Genis will do post-processing, which is displaying the results, perhaps which is the most interesting part you would like to get out of this process. You see, I did some initial preparations. I calculated the material properties. After you download Vector 5 installation software, you install it, and it's going to put Vector 5 analysis folder on your desktop. The process would start with Formworks Plus, as I mentioned before. That's the preprocessor. So you start Formworks Plus. It's going to be a new model. We are only going to be able to use Vector 5 because this installation is only for Vector 5. This is a new model. This is an existing model. So I'm going to create a new model. First of all, let's save it. That's the first step. Continuous beam. This is the test model. Call this beam. Let's start with section definitions. So I'm opening this. As I previously highlighted or calculated, I'm going to put F prime C 19.5. Other numbers I'm inputting 0 because program will calculate it based on default calculations. You don't have to do anything. No stirrups. So I'm going to do two different modeling. In the first model, there is going to be no stirrup as in this problem because the problem is only for flexural modeling. However, I'm pretty sure that we will see this would fail because there needs to be some stirrups. Let's see the results, and then we can do second model enabling stirrups because there is going to be two sections. One is for span, other one would be for the supports. That is good. It's a rectangular section. Color is good. If you want, you can change it. In the next section, I'm going to create the cross section, which is going to be 600 wide, 900 deep, clear cover 30. I ended up with 60 layers because it's a fiber model. It's going to slice the section into a number of fibers. 60 too much, 30 is good enough. So if 15 gave us 60, so if we go with 30 millimeters slice thickness or layer thickness, that should be good. The final section is to define reinforcement, 340. This is the ultimate strength. You can again multiply this by 0.85, 459. No need for other changes. This is the ultimate rupture strain, starting of the strain hardening. So number of bars 4. You can select the bar, or you can input the area, but because it's 25 millimeter diameter, each bar has 500 square millimeter. I said bottom 1. Once I add this, I see 4. You can see the distance, 857. So 900 minus 857, so it used 43 millimeter, which does make sense because I have 30 millimeter clear cover plus half of the diameter. I'm done. So section 1 is created. Keep saving it. I'm going to create section 2, but always an easy approach, just to copy it and call this support. This is going to be doubly reinforced. No change on this first definition window. The second one is support. Again, let's go with 30, 900. Let me just double check to prevent any mistakes. In the final part, again, we need to define reinforcement. This is bottom 1. It was 340, and this one 459. Bottom 1 support 825 m. You can input the distance. You don't have to use this drop down menu, but top one, bottom one is the location you want to be, because these are just after the clear cover. So no matter what, you are going to be having top one, bottom one, or one of those. This is going to be top one, and you see it's automatically calculated clear cover plus half of the bar diameter. So I can add that, and you can visually confirm. Next step would be sketching the beam. I'm going to be using auto meshing because it's a finite element procedure. There's going to be some meshing involved. All right, so the first step is to create the structure. For this, I need to input nodal coordinates one by one. I want 1, 2, 3, 4, 5, 6, 7, 8. I want 8 nodes because some of them will be change of the cross section. Some of them would be my support point. I start with 0, 0, and then 4800, 0, 8000, good, 11500, 14500, 18000, and then 23,000 would be my final. I'm going to assign a single cross section, and I'm going to change other ones later on because there is only 2 sections. It's easy to change later on. This would be faster. I'm assigning span, add region, so I edit the region. So this is the structure. Create mesh, add mesh to structure, done. Come to this glasses, get rid of element numbers, keep the node numbers in case needed. Let's put the supports because supports important. Roller, 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 and I'm going to fix rotation because axis of symmetry beam will not rotate. So if you take a tangent, that tangent on the deflected curve should be perfectly horizontal, so rotation would be 0. And also I'm going to restrain horizontal movement, node 48. So what I'm going to be doing, rotation restrained as well as delta x restrained. Select this one, add, and you see that node came to that point. Other ones, just a roller. This one, so you see x coordinate 2, you can just get it in the window. 18,000 would be the another one. Let's find 18,000. 5, so 3 rollers and 1. This is done. Let's assign the sections, but I want to use different colors. I didn't do it in the modeling, so because I have 2 sections with the same color, which is not good because I want to see the difference. So support, find something a little bit darker color. If I pick this one, that's good enough. Done. So now just find support locations and assign a different section type. Assign material type. This is the one. I want to assign support. It should start 4800. Starts from node 1 and I think node 3. 11, perfect. So that's exactly what I want. So this region I selected support, assign, yes, color changed. The other one would be between 4, which is 14,500, and 6, which is 21,500, perfect. Again, if you pick pointer, you have to select one by one because there is very many. It does make sense to go with the window option. Support, assign, yes. Almost done. What's missing? What's missing would be load application. When you are doing a nonlinear analysis, you do not want to do it for a single load value. You would always like to do a pushover because as you load the system gradually, you see the entire spectrum of responses. When is the cracking point? When is the reinforcement yielding point? Are there any shear cracking, any shear deformations, etc.? So you want to be able to see all of these versus just a single point. So for that reason, typically what I would like to do is at least 10 load stages. 120 is the target. If the structure is stable, if the structure is not failed at ultimate limit state, which is 120, it is going to be safe, it's going to be acceptable. That's what we are doing. We are checking design. So I'm going to be applying 12 kilonewton meter and load factor 1, so it's going to be increased. Load stage 1, it's going to be empty load. If you want to start with 12, you can do so. It doesn't need to be an empty load stage, but this is what I'm going to be doing, starting with 0, and it would keep going. It's not going to stop at 11. It would keep going until it fails. It might be more than that. Probably it would be more than that, and we will see the exact failure point. And these are different load cases. You can see point load, temperature load, etc., etc. But what I want would be uniform distributed load. You can see some information. So my situation is easy because it's fully loaded. I don't have this partial situation. So fully loaded, it's going to be A over L would be 0, B over L would be 1, which is the default case. You know, this is 0, this is 1. I'm inputting 12. That's easy, nothing else. Again, I would go with window, apply, done. So it shows UDL. UDL, you can always turn it uniform loads, none, apply, they are gone. Escape, if you click on escape, window will disappear. That's pretty much done. The final thing would be the load control. It's the job file, the first defined job. You click on it. Good idea to give this some name. Beam 1. These are optional. You can give the date, etc. But what's important would be initial 0, increment 1, final 100. Final doesn't matter. Put some big number. It's going to fail anyways. There is no way this could go up to 100. I'm expecting it's going to fail before 20 because 11 is the target. If you exceed it, it's not going to be 100. So give a large number. If you increase it by 1, this is what I'm doing. If you increase it by 2, it's going to be 0.24. That's too much. 1 is good enough. You don't have to touch anything else. You know, everything's set by default. This is a really sophisticated procedure only for reinforced concrete. You can see compression pre-peak, post-peak, compression softening, tension stiffening, tension softening, hysteresis response. You might say that this is a monotonic loading, but still some parts might unload, some parts might load, so hysteresis response might come into play. There is double action, reinforcement buckling, confinement. Not applicable, we don't have any stirrups, but you know, in the second part of the video that would be applicable. Dilation, which is Poisson's effects, cracking criteria, crack stress check, crack width check, crack slip check, etc. So basic is what you need. So I'm done. So the model is done. We are ready to run the analysis. Before any analysis, you have to save 3 different files. One is the structure file, load file, as well as job file. I'm going to select folder on my desktop called beam modeling, and I'm just saving 3 files. And then this runs vector program. So this is the processor, that's the main program which is running. So the program is running, and you can see, you can pause it for a minute. You can see each load case is done. You can see the convergence. It goes up to a certain number of iterations. It's a very iterative. There is a lot going on. It failed. Something happened. You can go back and you can see, I expect shear failure because we didn't put shear reinforcement. So members shear failure. Yes. So low stage 10, it failed. So 11 was the target. It's not going to make it. So it is not going to be a safe design, even using a nonlinear analysis, which typically gives you more capacities than your linear elastic analysis, which is highly idealized. Next step is the most interesting part. We will see the results. You have to start post-processor Genesis, which is this little icon from here. You can see a lot of people worked on this. I'm going to find beam modeling folder and click on vector job. This is the job file. It's loading it. So we got it. So this is the system. You see the same beam. You can hide node numbers, member numbers. You can see restraints. I'm just going to hide them for now. In 2 dimensions, this is a crack map. So if you see these colors, these are the crack widths, reinforcement yielding, it's blue colors, strain hardening, etc. So you can see all of these. I'm going to start loading. You can see crack pattern. If you want to see first cracking, it starts at load stage 3. So I'm loading this more and more. You can see these are crack widths, 5.8, and you see some diagonal shear cracking taking place. The last valid load stage, probably load stage 10, right before failure. I'm seeing reinforcement yielding do not take place, which is not something good. We want reinforcement yielding. So you can come to results. Let's take a look at reinforcement stresses. So these are reinforcement stresses. You can see this is layer 1. Layer 1 was the one which was at the very top. Maximum 251 megapascal, which is below yielding value. The yielding value was 340. Layer 2, that was the bottom layer, which is much less. So this is obviously not a good design. If you do a performance-based design using nonlinear analysis, this is definitely going to be caught in this nonlinear modeling phase, and you have to rectify the design. In terms of results, you can see concrete stresses. For example, principal compression. These are the stresses because you sliced each layer. If you zoom in and if you can see, I think this also shows member lines, layer lines, so you can see because each section you sliced it into 30 layers and each layer will have a constant stress. This is for load stage 10. You can look at 9, so each load stage corresponds to a different uniform distributed load intensity. You can come to results, concrete stresses, tensile. You can look at the tension, which is clearly above cracking stress. You can see displacement values in a performance-based design or in any design. Displacement is important, so you can really see the maximum displacement minus 8.8. What else you want to know would be the moment diagram. You can see this is the moment corresponding to load stage 9, and you can change it. Of course, you want the numbers, which is here, so you can see all the peaks. You can also see support reactions. So these are, you can zoom in 846 kilonewtons up from this one. If you want to see the shear diagram for every load stage, you can get that from this. Axial force shouldn't be. We put rollers, there's 0 axial force. If you want to see a single element result, so for that single member, you can see stresses in each layer one by one. You can, change load stage for different load intensity. You may wonder reinforcement situation. Usually you would pick the worst member and you investigate that member in terms of reinforcement, concrete stress, strain, etc. So if you come here, you will see top reinforcement this number, bottom reinforcement that number. So the member we selected not subjected to huge stresses in terms of reinforcement. So the entire beam not used efficiently because of shear failure. It fails prematurely. Before I finish this analysis, I would like to get the pushover curve, but before that I have to see what node. So I have to come here, close, node numbers, so it is 48. I need to come to this plot function, displacement y. There are a zillion of parameters, but typically displacement y is what you want to get. The other one, just load factor, is going to be 1, 2, 3, 4, 5, etc. 48 for the displacement. Include data. One of them, make it x-axis. Generate data. It would fix it itself, 11. So this is the data. You would just copy this data, go to Excel. This is again load stage 1, 0, 12, 24, etc. It goes on. This was my target, but clearly I didn't achieve that objective with this analysis. It is not acceptable, so it doesn't go there. Something like that maybe. You have to confirm 11. Is it a usable load stage? I need to look at convergence. Convergence, that is fine. Definitely 9 is fine. Let's look how it looks. Of course, we want to see cracked lines. Pretty bad. This is just failing. So at most 10, nothing more than that. The one, this is 48. That is pretty much it for the first part. In the second part of the video, I'm going to be adding shear reinforcement and then seeing what would change, whether it would change the failure mode, whether it would improve the load capacity. I would certainly expect so, because failing in shear and putting even the minimum amount of shear reinforcement will make a great influence in the results. So let's see that. To be able to add stirrups, I'm going to find the folder I saved my Formworks Plus model. I'm just going to copy it. Call this beam stirrups. This is the second model. So now I'm just going to start Formworks Plus. You can, once you install it, becomes one of your apps. You can go into your start menu, which I just opened it. It is coming up. I'm going to open. So you can see beam stirrups, which is what I created. The only thing I am going to be changing would be the section types. So we come here. Meshing might be needed because there is going to be clear cover plus stirrup thickness plus half diameter of the bar. So some dimensions would change very slightly. It's not going to change things too much. The problem I'm solving do not specify any shear reinforcement, but I am just going with some minimums. Probably it's not going to be enough, but anything would be better than the current situation. So I calculated that, which is 10 100 square millimeter at 300. So that's the minimum. Pick the one which is you think applicable. In the second screen you will see how it looks, but I would go with closed. This is already 10 spacing would be 300. Go with 340, and then again 540 times 85. This one is also 340. Just update this one, and it's warning you to do the meshing again because transverse reinforcement ratio is 0, but if you regenerate it will become very light. I mean 0.1%, which is nothing, which is minimum. I don't have to change anything. If you want to modify something, you can modify. You can see everything is adjustable. This 857, see, because I added stirrups, I need 11 millimeter. The stirrup has 11 millimeter diameter, so I'm just going to select button 1. It should automatically get that and update. See, it is good. That should be it. So I'm saving it. Again, I'm going to do the same for the support. You have to save it again. Beam stirrups, that's great, it's already automatically created. So I'm saving this, I'm saving that, I'm saving this one. Run the analysis. 10, 11, yes, it is going. So this will make it. So this would be fine. It failed, but after the ultimate limit state. Failed 14, that's good. 14, even 15. Again, shear failure because what we put wasn't enough clearly. You have to open Genesis, beam modeling, beam stirrups, node numbers, member numbers. Also, let's get rid of the supports. Oh, see, reinforcement yielding taking place, which is a good news. 11, yes, it is making it very nice. No problem with the ultimate limit state. It is stable, it is safe. Convergence is pretty good, 1.002. Getting into trouble, definitely 13, even 14 would be the low stage to cut, but let's get the data. That's what we want. Include, this is, it was node 48. You can plot it, but I want the data. It's going to fix it based on the load stages. Okay, 17. Just copy this. See, oh, that's very good. Where am I going to cut this one? We don't want a big jump. Definitely, I wouldn't go even this one, which, let's see. Can I take 14? Let's look at low stage 14. Is it something valid? If you see large gap in the horizontal distance, so you see you load it and it deforms at a certain amount, so far is good, but this is a little bit large. much larger, I mean double than the previous one. So I have some doubts about considering 14 or not. So if you are any doubt, it's still safe to be conservative. You can always get rid of that point. But let's look 14. Is it something acceptable? 14 is acceptable, but maximum, not 15. Or 6, you can get 14, which is fine. But this is definitely a little bit more conservative. So that's pretty much it. That's how you do your nonlinear modeling. This could be for a performance-based design, or this could be for an existing structure, because in existing structure, it's really difficult to pass. If you do the inelastic analysis, nonlinear will give you an idea. Is it failing in shear? Is it failing in flexure? What's going on? What are the loads? What are the crack widths? And you can make an appropriate decision depending on the results. That's it from me today. Thanks very much for your attention. Please do not forget to subscribe to the channel, like the video, and let me know what would you like to see in upcoming videos. Thanks very much. Bye for now.